Hello students. Now we begin our exciting journey into Unit 1, Introduction to Parallel Computing. And I want you to listen carefully because these are the most important and most expected questions for your semester examination. I am guiding you just like I do in class, slowly, clearly, and with full confidence, so that every concept sits firmly in your mind. First, we discuss the question, explain motivating factors for parallelism in computing systems. Parallelism exists because modern problems are very large and complex, and a single processor working alone takes too much time. When many tasks are divided and executed at the same time, the total execution becomes faster. Scientists, engineers, and businesses demand quick results, whether it is weather prediction, medical imaging, artificial intelligence, or big data analysis. Parallel computing also helps in better utilization of hardware resources, because instead of keeping processors idle, we make all of them work together. Energy efficiency is another strong motivation, because finishing work faster often consumes less power than running one processor for a very long time. Scalability is also important, because as problem size increases, we can add more processors instead of redesigning the entire system. Now, let us move on to our next important topic, scope of parallel computing. From this topic, we can expect questions such as, describe the scope of parallel computing. Give applications of parallel computing. Parallel computing has a very wide scope, because it touches almost every modern field of technology. In scientific research, parallel computing is used for simulations such as climate modeling, space research, and nuclear experiments. In business and finance, it helps in risk analysis, fraud detection, and high-speed trading. In healthcare, it supports genome analysis, medical image processing, and drug discovery. In everyday life, parallel computing works silently inside smartphones, gaming consoles, and cloud servers. Even simple tasks like video streaming and online searching depend on parallel systems working in the background. Because data size is growing continuously, parallel computing becomes not just useful but necessary. Now, let us move on to our next important topic, stored program computer architecture. From this topic, we can expect questions such as, explain stored program computer architecture with neat diagram. Stored program computer architecture is the foundation of modern computers. In this architecture, both data and instructions are stored in the same memory. The central processing unit fetches an instruction from memory, decodes it, and then executes it. This cycle repeats continuously. If I explain the diagram in words, imagine a memory block that stores programs and data together. This memory connects to the central processing unit through buses. Inside the central processing unit, there is a control unit that decides what operation to perform and an arithmetic logic unit that performs calculations. Input devices send data into memory, and output devices display results after processing. This design makes computers flexible because changing the program changes the task without changing hardware. Now, let us move on to our next important topic, impact of memory latency and memory bandwidth on system performance. From this topic, we can expect questions such as, explain the impact of memory latency and memory bandwidth on system performance. Memory latency is the time taken to access data from memory, while memory bandwidth is the amount of data that can be transferred per unit time. If memory latency is high, processors waste time waiting for data, which reduces performance. Even very fast processors become slow if they cannot get data quickly. Memory bandwidth also matters because when many processors request data at the same time, limited bandwidth creates congestion. This situation is very common in parallel systems. High latency and low bandwidth together create a serious bottleneck. Therefore, system designers use techniques like caching, prefetching, and memory hierarchy to reduce these effects and improve overall performance. Now, let us move on to our next important topic, cache memory. From this topic, we can expect questions such as, Write a short note on cache memory. Cache memory is a small, very fast memory located close to the processor. Its main purpose is to store frequently used data and instructions so that the processor does not need to access slow main memory repeatedly. Cache works on the principle of locality, which means programs tend to reuse the SAM data again and again. There is temporal locality, where recently used data is used again soon, and spatial locality, where nearby data is accessed together. By using cache memory, system speed improves significantly, and memory latency impact reduces. Now, let us move on to our next important topic, implicit parallelism. From this topic, we can expect questions such as, explain implicit parallelism with suitable example. Implicit parallelism means parallel execution happens automatically without the programmer explicitly writing parallel code. The compiler or hardware identifies independent instructions and executes them simultaneously. For example, if two arithmetic operations do not depend on each other, the processor can execute them at the same time. This makes programming easier because the developer focuses on logic while the system handles parallel execution. Now, let us move on to our next important topic, dichotomy of parallel computing platforms. From this topic, we can expect questions such as, explain dichotomy of parallel computing platforms. The dichotomy of parallel computing platforms refers to the division between shared memory systems and distributed memory systems. In shared memory systems, all processors access a common memory space. In distributed memory systems, each processor has its own local memory and communicates using messages. Each approach has advantages and challenges related to speed, scalability, and complexity. Now, let us move on to our next important topic, uniform memory access and non-uniform memory access. From this topic, we can expect questions such as, describe uniform memory access and non-uniform memory access with diagrammatic representation. In uniform memory access systems, every processor accesses memory with the same delay, no matter which memory location it uses. This design is simple and predictable. In non-uniform memory access systems, memory access time depends on the location of memory relative to the processor. Local memory is accessed faster than remote memory. If I explain the diagram in words, imagine processors arranged in groups, each group closer to certain memory modules, making access faster within the group and slower across groups. Now, let us move on to our next important topic, message passing costs. From this topic, we can expect questions such as, explain message passing costs in parallel computers in parallel machines. Message passing costs include the time taken to send and receive messages between processors. This cost depends on latency, bandwidth, and communication overhead. When messages are small, latency dominates. When messages are large, bandwidth becomes important. Synchronization and copying data also add to cost. Efficient communication is essential for high-performance parallel systems. Now, let us move on to our next important topic, communication costs in parallel machines. From this topic, we can expect questions such as, write note on communication costs in parallel machines. Communication costs refer to delays caused by data exchange between processors. These costs include startup time, transmission time, and waiting time. If communication is frequent and inefficient, system performance reduces drastically. That is why algorithms are designed to minimize communication and maximize computation. Now, let us move on to our next important topic, levels of parallelism. From this topic, we can expect questions such as, explain different levels of parallelism in parallel computing systems. Parallelism exists at multiple levels, including instruction level, data level, task level, and program level. Instruction-level parallelism allows multiple instructions to execute simultaneously. Data-level parallelism processes multiple data elements at once. Task-level parallelism runs different tasks in parallel. Program-level parallelism executes independent programs together. Each level improves performance in a different way. Now, let us move on to our next important topic, SIMD and MIMD architecture. From this topic, we can expect questions such as, explain with suitable diagram SIMD and MIMD architecture. SIMD architecture means single instruction multiple data, where one instruction operates on many data items at the same time. Imagine one control unit sending the same instruction to many processing units, each working on different data. MIMD architecture means multiple instruction multiple data, where each processor executes its own instruction on its own data. This model is very flexible and powerful. Now, let us move on to our next important topic, data flow models. From this topic, we can expect questions such as, write a short note on data flow models. In data flow models, computation happens when data becomes available. Instructions do not follow a fixed sequence. Instead, they execute as soon as their input data arrives. This model exposes a high degree of parallelism and avoids unnecessary waiting. Now, let us move on to our next important topic, demand-driven computation. From this topic, we can expect questions such as, write a short note on demand-driven computation. Demand-driven computation means computations are performed only when results are required. Instead of computing everything in advance, the system computes values on demand. This saves time and resources, especially when some results are never used. Now, let us move on to our next important topic, superscalar architecture. From this topic, we can expect questions such as, explain basic working principle of superscalar architecture. Superscalar architecture allows a processor to execute multiple instructions per clock cycle by using multiple execution units. The processor fetches multiple instructions, checks dependencies, and executes independent ones in parallel. This improves instruction throughput and overall performance. Now, let us move on to our next important topic, multi-core and multi-threaded architectures. From this topic, we can expect questions such as, explain multi-core and multi-threaded processor architectures with suitable diagram. Multi-core processors contain multiple processing cores on a single chip, allowing true parallel execution. Multi-threaded processors allow each core to handle multiple threads, improving utilization. If I explain the diagram in words, imagine several cores inside one processor chip, each core capable of running multiple instruction streams. Now, let us move on to our next important topic, VLIW processor. From this topic, we can expect questions such as, what is VLIW processor? Write any two advantages of VLIW. VLIW stands for Very Long Instruction Word. In this architecture, a single instruction contains multiple operations that execute in parallel. The compiler decides which operations can run together. Advantages include simpler hardware and efficient parallel execution when the compiler is well designed. Now, let us move on to our next important topic, N-wide superscalar architecture. From this topic, we can expect questions such as, explain N-wide superscalar architecture with advantages. N-wide superscalar architecture means the processor can issue and execute multiple instructions in parallel in a single cycle, where N represents the number of instructions issued together. This increases instruction-level parallelism and improves performance. Advantages include higher throughput and better utilization of processor resources. With this, students, we complete Unit 1. And if you revise these explanations carefully, you are absolutely ready to face your semester examination with confidence and clarity.